Thank you for the opportunity. Thank you for the opportunity to let me to talk about my favorite topic at the moment. So yeah, I'm Gergely Gálfi, and I'm working on my PhD at Ötvös University on computer science. So I'm practically a renegade physicist, but I will not talk too much about physics today, rather about software ergonomy. So even I don't want to say that I'm coming up with some very new theories, rather that how to approach well-known problems, but which, as far as I see, not too many there to really to realize practically and try to run it on a available quantum computer or a quantum computer simulator. So as I'm a PhD student, I have two very kind advisors. One of them is Dr. Tamás Kozsik, and the other one is Dr. Zoltán Cimborás, who at the moment is not yet, he already left Wigner Institute, but and he's working now in Helsinki. But in the time when we are working on this thing, he was entirely associated with the Wigner Institute. So yeah, what I will be talking about, as the title says, it is some sort of language or framework. And obviously, I want to say a few words on the motivation for developing yet another language for quantum computers. And the main point here is that we try to employ Markov chain Monte Carlo methods on quantum computers. I don't want to go into the details. It is a totally different topic. But I want to emphasize the features in the Monte Carlo methods, which were important for us and which has driven us to develop a framework for generating some quantum algorithms. And the important thing in Markov chain Monte Carlo methods is that how we select our strategy to make small steps to find the peak of the probability distribution and mostly walking around that probability distribution. And obviously we would like to employ Markov chain Monte Carlo methods on quantum computers. So we first began with some very simple quantum algorithms. One of the most simplest one is the quantum Fourier transformation, QFT. And for that, we were relatively easily find a nice and very effective small step strategy. And yeah, the next question is that, okay, but QFT is a very, very nice operation. It has a lot of symmetries. One of the most beautiful unitary transformation in both, so in linear algebra practically. So, and obviously most of the interesting quantum algorithms are derived some complicated classical algorithms like hashing algorithms or linear congruent generators, and so on and so on and so on. So the question was that what happens if we have a less symmetric unitary time development of a quantum computer? And for that, we needed a tool which able to generate such a time development. So we didn't want to play around with some random unitary transformations. We wanted to have some unitary transformations which are coming out from some real algorithms. So that was our motivation to have such a tool set. And the not so selfish motivation is that, yeah, we are, as I said, that I'm rather working at the moment as a computer scientist. So I'm a passive user of quantum computers, and I'm eagerly waiting for the situation when there will be quantum computers with 10,000s or 100,000s available logical qubits. And I want to be prepared for the situation when, yeah, we have the practically usable quantum computers, and we would like to translate classical algorithms onto quantum computers. So yeah, one of the typical use case for such frameworks is the Shor's algorithm, which is partially a cleanly quantum unitary time development, but it includes a unitary time development coming out from a classical problem. It is this calculation of a modular multiplication. And in the case of Shor algorithms, these numbers A and K and even N is a classical numbers, but Y is some built up from some qubits. So you may expect that even the result will be a quantum quantity or qubit-based integer. And yeah, it is easy to write this down, but yeah, if someone asks that, okay, but please provide me the sequence of C-nodes which are producing this algorithm, then it is a more difficult question. And yeah, that is what we aimed for, to have such an algorithm that I write this down as a programmer, and a unitary sequence is coming out from the framework. So yeah, there were a few options here. We decided to move on to create an entirely new language instead of extending Python or whatever language with some features which can generate also the unitary transformation. And the name is, as was mentioned in the title, it's Qubla, which is not very complicated. It's just abbreviation for qubit language. And to tell what exactly Qubla is doing, first I remedied that how what is the difference between interpreter and the compiler. Interpreter is a very simple thing. That is what the people who are beginning to learn programming are first encounter. You type a program or even one a single statement, and it is immediately executed. And if you type the next statement, then it is also evaluated and executed in real time, practically. So obviously, one of the main advantage of the interpreter is the simplest. So yeah, we can count here Bash, for example, or basic language, which was for me the very first language which I encountered. And there are a lot of JavaScript. And the other way of generating something or doing something with a computer is to use a compiler. When you have maybe exactly the same code, but it is first translated to a so-called bytecode, which is not necessarily humanly consumable, but it is very well usable for a real or a virtual machine. And when it is already compiled, then it could be executed on that real or virtual hardware. And the main advantage of the compiler, the reason why we take up this complication is that it could be highly optimized, because the compiler views the entire code and do all the syntactic and semantic analysis of the code first, and then comes up with a highly optimized and very usually way faster bytecode than what we could get out of an interpreter. And why is it important for us? Because Qubla could be seen as a superposition of the interpreter and the compiler. And the reason why it happened here is not to create some bad jokes on quantum physics, but yeah, we practically will have two different outputs. So when it encounters a classical calculation that calculates 1 + 3, then it is executed immediately. And when it encounters a statement like this, where one variable is built up from 3 qubits, so this is the definition of a 3-qubit integer in Qubla, which should have the initial value of 5. Then when it evaluates this expression, it recognizes that, okay, before this plus sign, there is a quantum quantity. So it not only does the calculation, which obviously will, the result will be only that, okay, it contains some qubits, but it generates the unitary sequence, the unitary chain, by our terminology. So practically, it is running as the interpreter on the classical statements, and all which could be done classically, it is executed. But simultaneously, this unitary chain is built up, and when the compiler finishes with the code, then we get not only something on the console, but we get simultaneously an object, which is a chain of these unitary operators. And so, yeah, it is worth to look into a little bit more detail into this unitary chain. What we have here is a very, very high dimensional set of state, or one initial state of a very high dimensional Hilbert space, usually finite dimensional, but if we have 100 qubits, then the dimension is obviously 2 to the hundredths power. So it could be very high dimensional. And these individual unitary operators are acting on that very, very high dimensional space. So you may ask that, okay, how I can handle such a large unitary transformation? The good news is that all these usual classical algorithms, addition, subtraction, comparison, are built up from atomic steps which only act on a few number of qubits. I mean, few that the atomic steps are usually not acting more than 6 qubits. But usually it is, or frequently it is even smaller. And I put here the expression how it looks like when we have a unitary operator which obviously acting on the whole Hilbert space, but practically acts only on in this example only on the second and the third qubits, and it's a little bit looks complicated, so it is better to look at the graphical representation of it. And believe it or not, this friend will be happy to recognize it or even know it, that this is a Feynman diagram of the quantum evolution of the or the unitary evolution of the quantum state within our quantum computer. So yeah, it is much better to look onto this problem with this graphical representation instead of these complicated expressions. And yeah, the important thing is that when we are try to store these unitary operators, we only have to store relatively small matrices. As I said, that the inverse case, it would be a 64 times 64 dimensional unitary matrix or complex matrix. And how exactly this unitary transformation should be defined? One option is that, yeah, pick an arbitrary unitary transformation up to your choice, which acts on a few number of qubits. The other one is that I say that I want that this unitary transformation implements a Boolean function. And in the simplest way, the input and output bits for that Boolean function are having the same number, it having the same number of input and output qubits. So the definition is almost natural that, okay, if I have a canonical base state, then the unitary transformation should act on that canonical base state as it would act as a function on the individual or on that set of input bits. And obviously we can generalize this definition for when we allow that the input and the output number of input and output bits will be different. in this case, we have to do some trick because there is no such option for a unitary transformation to have different output dimension as for the input dimension space. So we are somehow arbitrary padding this thing. The simplest padding is that putting zeros everywhere where there are fewer bits than on the other side. So it could happen that if we have more input bits than output bits, then we are padding the output states, or if we have more output bit than input bits, then we'll do some padding on the input state. What is also important that unitary operation is not only having a same input and output dimensions, but also it has to be invertible or injective. And it could be achieved with this specific padding that it is a sufficient necessary condition that if f itself is an injective function, then the u will be also a injective linear transformation as well. And because of the definition, it will automatically provide unitarity as well. So yeah, it will be important later, this thing that finally we need to make our Boolean functions in some sort of injective functions. And what was very important, and I want to emphasize that when we developed Qubla, we intentionally try to avoid anything which comes with the following of the quantum state evolution itself. What we are aimed at is to have a very well-defined sequence of unitary operators, but we didn't want to simulate that how these unitary operators are affecting that selected state. Because our goal was to feed a real quantum computer with this information and let the quantum computer do the dirty work of calculating the final state of this system. That comes with a very strong restriction, and that shows that, okay, Qubla is not a universal tool. It focuses only on the unitary, defining and optimizing to some extent the unitary time evolution. But for example, measurements cannot be supported in Qubla. So yeah, when someone has a quantum algorithm which uses some measurements, and most of the quantum algorithms are using measurements, obviously, then that should be done outside of Qubla. So yeah, Qubla generates the unitary evolution. Please feed it to a real quantum computer or simulator, do the measurements there, and based on the result, you can either give some new inputs for Qubla and generate a new unitary evolution, or do the work outside of Qubla. So hey, Qubla was never intended to be a general tool. It focuses strictly only on the unitary time evolution of a quantum computer. Another problem which I want to mention it briefly is that the problem of invariance. And what does it mean? If you have a very simple program like this, classically, it is quite clear that when we are running this, then we put 5 into x, then we put 5 plus 1, so 6 into y, and we put 5 minus 1 into z. But in quantum computer, when we have a qubit corresponding to variable x, and initially it contains a state which corresponds to the integer number 5, then obviously if you and we apply a increase by 1 operator on that set of qubits, it will change the state actually. So it will not contain anymore the state corresponding to 5. It sometimes happens that even it will become entangled with other qubits, and we even cannot determine that which base state it corresponds, because it is in a mixed state. But sometimes in a real code, we are referring back to the same variable more than once. So we have to somehow first of all, keep the invariance of these variables. And the invariance just means that, okay, if I have some qubits assigned to some variable which should be kept, all the operators are acting on that qubits, that they are not changing the classical state of that of that variable, and it could be defined in a much nicer way, that you may say that the density matrix for that specific qubits density matrix will not change for that specific qubits. So, and the way how we can solve it is that simply add these qubits to the outputs of the Boolean functions. And just a little word about Qubla syntax. So one reason why we created a totally new language, because I wanted to have a special function definition where we put emphasis on the truth table of a Boolean function. So normally you define a function that in a way that you just write a script for that. But the other option is that define a function just by defining the truth table. So what should be the, for what input bit combination, what should be the output? And I show you a short example that how Qubla handles these truth tables, because that is the key feature of Qubla, that how it works on truth table Boolean functions, or Boolean function based on truth table. So let's assume that we have a truth table for the addition, 3-bit addition. So practically these three are the input bits, and here we can see the sum, and here we can see the carry bit. And what is even more important, that when we call this function, let's assume in Qubla, then the first bit is called with a classical number. We know that it is 1. And the two other will be qubits. So only on the second and the third input bit it will act on a quantum quantity. So the very first step what we can employ here is to simplify the problem. This is, you can see it as some sort of pre-calculation, is that we pick only the lines where the first bit is 1, because we know that the first bit is 1, so the lines beginning with 0 are not interesting for us. So immediately reduce significantly our truth table. And also some other simplification could be done here to search for constants, columns, and other stuff. I don't want to talk too much about it. But what is very important here is that I said that the final resulting object should be a unitary transformation, which requires this function should be invertible. But we can see that these two lines are the same, so the two output lines are the same. So it's not invertible. What can be done here is to add some additional qubits, which splits up these equal lines. So after adding this appropriately selected output bits, it became an injective function. And what is also very important in Qubla, that you can use it for reducing the transformations. Because as you have seen that it is quite greedy on qubit usage, and obviously we would like to reduce it. One way to do that is that if we are saving a qubit to be invariant, but it's never again used, then we simply get rid of it, like this one. Or it even happens that there is a unitary transformation, or a Boolean function based unitary transformation, where none of the output qubits are used anymore, and we can delete it. And what is also very important here is to we have a capability to join individual steps and building up obviously a little bit higher dimensional unitary transformations, but also we can save a lot of qubits on it. And what I still want to talk about, because it is available with the open source code of Qubla, is the application on Shor's algorithm. And the difficult part of Shor's algorithm is to find the shortest period of this function. So it is a modular exponentiation. And this is the usual architecture for Shor's algorithm. So this is where the classical function is translated. The classical modular exponentiation is translated into into a quantum circuit. And this is how the code looks like for Shor's algorithm. And what I want to mention here is that after doing all these, the compilation and the unitarization, we end up with a quantum circuit which has only 18 qubits and one single quite large true stable step, which could be run without any difficulty. And yeah, you can see with your own eyes the full Shor's algorithm, how it works and how it could be derived from a source code. So thank you for your attention, and I recommend to look up the GitHub page of Qubla, because you can find, for example, the Shor's algorithm in a Python notebook, and you can play around with the parameters of your choice if you want to. So thank you for your attention.
Thank you very much, Gergely. Questions? I think it's still after lunch thing, but I would have a question, and I'm not very familiar with all of this compilation and other things from the theoretical point of view, but I can imagine that this is a kind of injection. So this is one directional. So you have your programming language and you translate this to some certain computing architecture level, other language, I would say. And this you cannot do to the inverse direction typically. This is why reverse engineering is a big business and it's not straightforward. But at least in your case, can you recognize in the reverse way that what could be the non-quantum and what could be the quantum part? So can you do the forward, at least just that level that you can say that this is and that is the...
It wasn't an aim to be able to reverse engineer.
No. I'm just asking this in general.
But yeah, so based on the output of Qubla, I definitely can identify that which part, for example, the Shor algorithm is the.
But it's not because you have a kind of lightweight code at the moment. So in a complex code, it could be not straightforward, no? Am I right?
So what is important in Qubla, I didn't mention it because it is, or just very briefly mentioned, that technically we handle two different types of unitary transformations. One is an arbitrary unitary transformation, just a set of complex numbers obeying the unitarity condition. And the other one is that this unitary transformation should come from a Boolean function with this truth table. Okay. And actually the truth table is held there. And if you see the truth tables, you can very easily recognize that, okay, where some addition is happening, where some, or in the original code, where was a comparison, less than operation, because they have their typical truth tables. So for example, when we're talking about addition, usually most of the, all of the transformations are these 3-bit additions, but some of them are simplified because some classical or constant value are fed into it and not a qubit. But yeah, if and the same applies for the comparison. Comparison has its typical truth tables, and you can recognize it. But this comes from the feature of Qubla that in its output product it kept this information, that what is a general unitary transformation and what is a transformation coming out from a truth table or a Boolean function. Yeah. So yeah,
Okay, thank you. Any further questions or remarks, please?
Sure. Thank you so much for your talk. I'm curious. So you've given the example of Shor's algorithm, and there are cases where you would like to factorize numbers which can be really big, and your for loops might have lots of looping, for example, to do. So the instructions might already start to increase very, very much. And once you start to load this program, there's already overhead in the classical pre-processing of the program itself. I'm curious because there are some packages that are trying to solve this by going into the LLVM layer or trying to do something with quantum intermediate representations. Are these also criteria that Qubla is considering, or are these being solved or regarded in Qubla?
So what I was aiming at in case of Shor's algorithm is that to have a, so first of all, the algorithm itself, the Shor's algorithm itself is quite friendly regarding the number of the quantum steps. Okay, so it is polynomial regarding the original bit number, and in that sense, Qubla can create the unitary sequence or the quantum circuit for a very large Qubla program. So what could be run obviously should be a small one, but you can generate a large, for example, for 200 bits, you can generate practically within a matter of few 10 seconds the actual unitary sequence. So these operators you can generate individually, and also the operators working within the quantum Fourier transformation. But obviously you will not be able to run it because at the moment we don't have. So you will get a definition of a quantum circuit which has I don't know 100,000 qubits in the case of 200 input bits, and obviously it will have again a few 10,000 steps, individual steps. But if you have a quantum computer which can endure that task, where it has 100,000 qubits and it can remain stable or keep up the coherence for again a few 10,000 steps, then Qubla will provide the steps to be executed. Okay, so Qubla can create the quantum circuit, but it obviously cannot is to run it. Even there is, as I said, no attempt within Qubla to run the individual algorithm. And what it aims is just to take the classical code that I need here a modular exponentiation, I need here an addition, and so on and so on and so on. And it will convert it into a sequence of well-defined unitary transformations. So, yeah.
Okay, thank you, Gergely. I think you can continue this in the coffee break. So thanks again.
Thank you.